This is the third and last video in this series. These videos are designed to provide an overview of concepts that led up to the development of quantum mechanics. Viewers are encouraged to learn more in depth about each of the topics discussed here. In this video, we finally find explanations to many of the enigmas brought up in the previous videos. What are atoms and what is inside of them? How can we explain black body radiation? How can we explain the photoelectric effect? How can we explain the discrete emission lines of atoms? How should we think of electrons inside an atom?
We now get to a number of experiments, very important experiment. First, Rydberg's formula. Rydberg's formula, he comes up with a formula that is very similar to Balmert's formula, except that he finds that if he uses wave numbers, which are proportional to 1 over the wavelength, all of a sudden the formula becomes very simple. And he can explain all of the different lines from hydrogen. Not only that, he can explain the lines from alkali metals. And that was a huge advancement. However, there was no fundamental theory. It was just a great simplification of the formulas. Okay? Thomson identifies the particles in the cathode ray as being 1,800 times lighter than hydrogen and having a negative charge. So what is hydrogen now? A negative charge that is very light with a positive charge in the center. Now we're beginning to see electrons, protons, and the discovery of radium and polonium, the discovery of neutrons. Okay? So this from 88 to 98, we have now the composition of atoms. Okay? Okay, what else do we have? So electrons identified, and radioactive compounds confirm the makeup of the nuclei. Okay, so at this point, we're at the end of the 1800s. We know that atoms are made of light negative particles, not yet known as electrons. We have a heavy nucleus that is positively charged. We know sufficient physics to calculate the motion of the particles and the potential energy caused by their electric charges. We know atoms emit light at discrete wavelengths. We know chemical properties depend on the number of valence electrons. And we don't understand black body radiation. We don't understand the quantized energies of the atoms. And we don't understand the photoelectric effect. Okay? So that's how we start the 1900s. Okay, remember the formula from Maxwell and Boltzmann with this 1/2 mv squared here? Well, Planck was trying to understand the black body radiation, and he may have seen that it looks very much like the Maxwell-Boltzmann distribution. And by playing around with some numbers, he came up with e to the h nu divided by k Boltzmann T. Okay? Now, you can say, well, this is not the same formula. Wait. 1 over this is e to the minus energy over k Boltzmann T. So all he did is he said the energy being emitted in this black body radiation must be proportional to some constant, which he called h, times the frequency of that light. The proportionality constant, h, is now known as Planck's constant. And that's how it came about. Okay? So the beauty is that this explained the entire curve of the black body radiation, allowed people to calculate what the maximum wavelength would be, and that's how we can tell the temperature of distant stars and all sorts of things. So that's from Planck. By the way, he called this a mathematical hack. Even though we now look at this and we say, Well, there's energy divided by K Boltzmann T, there's energy divided by K Boltzmann T. Yeah, but he called this introduction of a constant a hack. And he was not very happy about it. Okay? But then, again, Einstein said, well, there is this black body radiation problem, gets solved by Planck, must be that Planck is right, and here's energy divided by kBT, here's energy divided by kBT, therefore the energy of the light is E equals h nu. Pretty clever. And then, in the photoelectric effect, the energy of the photon needs to be greater than the energy needed to extract an electron from the metal surface, known as the work function. And so that solves the photoelectric effect, which, by the way, that's why Einstein got the Nobel Prize. And he did not get the Nobel Prize for relativity for pretty bad reasons, which all of you are welcome to read about. And electricity is now explained in terms of elementary particles such as electrons, because electric charge is quantized, discovered by the oil drop experiment by Millikan. So the first decade of the 1900s, big jumps. E equals h nu. We understand the photoelectric effect. We now have identified that electricity is quantized and it moves in these electrons, which we know that are lighter. Everything is now falling into place. But how is the atom made up? You know, if I have something solid like this, how are things put together? And so Rutherford shot some alpha particles, which are helium nuclei, and because he was working with radioactive compounds, he had access to alpha particles, and he found that most of them went through, except that some seemed to hit something quite massive. Okay, this was a gold foil, so the nucleus of gold is quite massive compared to the nucleus of helium, and so he figured that pretty much atoms are vacuum, and that all the mass is concentrated in the nucleus. Okay, so that's a big jump. And then we have another huge jump, that the orbits of these electrons must look like planetary orbits, and that jumping from one orbit to the next must be similar to kind of like those string instruments where you have those like quantized energies. And what was cool is that Bohr put some standard constants. He used Planck's constant here, and he was able to show that Rydberg's constant, which had explained the hydrogen lines, the emission lines, all of a sudden he could come up with it from kind of first principles if you assume that electrons have these kinds of orbits. Okay? And finally, we have an experiment where they shoot electrons and they look at the current of the particular gas, and they find that the current doesn't just monotonically increase, but it increases and then boom, drops. Increases and drops. Okay? What is happening? Well, if you remember in the photoelectric effect, you shot light and then certain wavelengths of light created electrons to be emitted, and so the spark was brighter. In this case, you shot electrons with greater and greater energy, so this voltage is the acceleration voltage. And then if you match certain energy levels of mercury, which is very easy to make into a gas phase, all of a sudden you match the energy levels and you have a big drop in the current. Okay? So this showed that not only hydrogen, but atoms have these discrete energy levels. And by the way, photoelectron spectroscopy is really useful to understand how the electrons are arranged And as we will see in quantum mechanics, they're arranged in orbits and or orbitals and all these things, and their energies, relative energies, can be studied with this type of spectroscopy, which comes from 1914. Okay, so what were the chemists doing? So in 1916, well, starting in 1904, the concept of coordination number and valence from Abegg, who noted that the difference between the maximum positive and negative valences of an element is frequently 8. Okay, so in 1916, Lewis used Abegg's insight to formulate his cubical atom and the rule of 8, which began Lewis dot structures. And so here's the Lewis dot structure of a few elements, and it's useful to make kind of molecular Legos and figure out how some molecules might be bonded. However, this is based on the idea that atoms are cubic, which really makes sense in some way. Okay, we have a few other interesting experiments. I mean, we now understand that it must be electrons going around the nucleus in an atom, but we were missing something that nobody expected, which is that electrons have spin. And this was done by Stern-Gerlach experiment. So they put silver in an oven, and the gaseous silver atoms came out, and then as they passed through a magnet, they deflected into one to the north and one to the south, according to the electron spin. Yes?
They didn't know that spin existed, then why were they trying to do this?
So the question is, why did they even do this experiment if they didn't know about electron spin? Well, because because Bohr had just proposed that atoms have electrons spinning around in a certain sense of an atom, and they were trying to figure out whether are they spinning in one direction or another direction. And I think that that's what they're thinking of why to do this experiment. Okay, so at the time, we have Heisenberg in 1924 writing about the quantum theoretical reinterpretation of kinematic and mechanical relations. 1925, published in 1925. Okay, pretty amazing. This is before Schrödinger. Okay, so we're almost there. And Born formulated the now standard interpretation of the probability density as psi star times psi, as being a probability density. Okay, and here we have, I think, one of the most important contributions in 1924. In 1924, we have Louis de Broglie and or de Broglie. He proposes that particles such as electrons and others possessing mass can also behave as light waves. Meaning, if light can be both particle and wave, then maybe electrons can be particle and wave. So this was a strange proposal. But he said, look, takes E equals PC. By the way, PC is the same as MC squared. Okay, P is the momentum. E equals PC from Einstein. Take E equals h nu from Einstein with Planck's constant h. Equate PC equals h nu. Okay, must be, right? I mean, this is not very complicated math. And if you then take that nu equals c over lambda, the frequency of light, you get that lambda equals h over p. That was his thesis. Okay? And his advisor didn't know what to do, so he sent it to Einstein, and Einstein said, almost as Spock would have said, fascinating. Right? Einstein just said, very interesting. Yeah, he didn't get the Nobel Prize, and this implies that particles, this is the weird part, particles with mass, like this object, can interfere constructively and destructively. That means that I can set up in principle like Young's double slit experiment with electrons or with atoms, and they're going to constructively and destructively interfere. Pretty amazing. but in search of a proof. The proof came from Davison and Germer, who were doing electron diffraction, and they were doing electron diffraction on an amorphous metal. And the story has it that as they were opening the chamber and changing things and cleaning and whatever, the surface of nickel got oxidized, and the oxide grew as a single crystal, and they observed maybe not this beautiful electron diffraction, but they saw diffraction spots, which meant that the electrons were going through multiple Young double slits in terms of atoms, and that there was constructive and destructive interference. And this, around the same time, almost in coincidence, proved de Broglie's hypothesis. Okay? So now things come together in a hurry. Heisenberg in 1925 solved what's known as the mechanical oscillator, or the quantum mechanical oscillator, or the harmonic oscillator. Very important problem in quantum mechanics. Schrödinger solves the hydrogen atom in 1926 and is able to reproduce the energy levels of hydrogen, which was unbelievable. The uncertainty principle is formulated by Heisenberg in 27. Photons are named. And in 1939, we have the discovery of nuclear fusion. Fission. Fusion comes much later. Fission. Okay? And this is the people, and you will recognize a few of the faces. And this is the Solvay Conference of 1927. And this is a huge success for science and our understanding of nature. Because if you remember, we didn't understand black body radiation. We didn't understand the photoelectric effect. We didn't understand why light from hydrogen atoms is quantized. And all of a sudden, everything comes neatly together thanks to contributions of many, many scientists over almost 200 years. So that's the summary. And what happens after? From valence bond theory, we go to molecular orbitals, to VSEPR, and then to quantum chemistry, continues to evolve. And now with the aid of computers that are super, super fast, we can now calculate entire molecules and their energy levels and vibrations and rotations and everything and all of their properties, and in a way that they correspond to experiments, sometimes as closely as the experimentalists can measure. So in a sense, in this review, you can see how we didn't know really what atoms were, some mishmash of positive and negative charges, to then Jimmy Neutron's idea of electrons orbiting, to then spherical orbits, to then orbitals. Okay? So my hope is that this video has piqued your curiosity about many of the topics touched on here, and that you will investigate what is already known from publications, and furthermore, that you're motivated to contribute with new scientific findings, because there are still many things that we don't understand in nature. And I think it's important for us to transmit what is known, but also to take what is known and consider the implications, and then taking it the next step.
Summary of part 3. We saw the first formula that explains the emission of alkali vapors and hydrogen atoms. Electrons and protons are finally identified, including their charge and their mass difference. Nuclear radiation provides information about the makeup of nuclei. Planck provides a formula that explains blackbody radiation, implying the existence of photons. Einstein uses the concept of photons to explain the photoelectric effect. Atoms are found to be vacuum except for the very small nucleus containing most of the mass. Lewis dot structures are developed according to the law of octaves. Spin is found to be quantized. Particles are proposed to behave as waves, and the wave nature of electrons is experimentally demonstrated. By treating particles as waves, quantum mechanics is developed and found to agree with experimental findings. you are now ready to dive into quantum mechanics with a better perspective of the observations and concepts that led us to that theory.